dioxide. I want 2 more of that make up the most of the air in the atmosphere.
Helium?
Not helium, trace amounts of helium. We're actually running out of helium shortage. And yet, Thanksgiving Day parade still can fill them, so I guess it can't be that bad. I'll give you a hint. I actually get into a debate with one of my coworkers about this not actually being a gas, but in my opinion it is. It has to do with the water cycle. Okay, it's not ice and it's not water.
Hydrogen?
Well, hydrogen is a part of this, mixed with the oxygen to make water vapor. Okay, so the clouds, right, is mostly made up of the gaseous state of water. There's water vapor, but he told me vapor is technically not a gas, and you'd have to ask Google. I don't have enough of a degree for that one. So, and then there's the 4th one, nitrogen, and that's the one we're going to play with today. Let's talk about water vapor, though. So, if water vapor is in the air, it's obviously a gas, right? Close, or depending on if you ask Elliot or not, but it's in the gaseous state, okay? Now we know if we wanted to turn water vapor back into a liquid, what do you have to do to it? How do you get the water from a gas to a liquid? Anybody know? One very specific thing you got to do to it.
The water joins together and then it falls down.
Yes. How does it come together? What has to happen to it?
It comes together. 2 droplets come together.
Yeah. Why did it come together? Why didn't it stay a gas?
Because there's a lot of pressure, too much pressure in the air.
Well, it slowed down, right? So how come the water in the air, those molecules turn into droplets by slowing down? What do we have to do to the gases? We have to make it colder. Okay, that's all you've got to do. You've got to make water vapor colder to turn it into a liquid. Okay, so I need a demonstration right now. Let's have, who wants to volunteer for me? You're really excited. You come on up. You too, come on up. What's your name? Everybody say hi to Kieran. And this is? Everybody say hi to Ario. All right, come on over here. You guys are going to be water vapor molecules, okay? Now, do you think that you guys are going to be close or far? What do you think?
Close.
What do you think? No, far. Get far away from each other as possible. Gas molecules are very far, far, far away from each other. 99% of gas is space. There's just a little bit of H2O over here and a little bit of H2O over here. Now, gas, do you think it's moving fast, gas molecules, or slow? What do you think?
Slow.
No, it's the opposite. It's fast. So I need you guys to move fast for me. All right, so no, don't, in place. So kind of shake around right now. Kind of go fast. Go fast, 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 fast. Now I'm going to slow you down. Now start slowing down. Right, you keep going moving though. Keep moving. Now I'm going to slow you down. As you slow down, start getting closer together. This is what happens, a little faster. This is what happens to all gases once you cool them down. I'm making them colder. They get closer together, stop right there, and then they become a liquid, okay? Eventually, if they got super cold, get really close together and lock arms. Lock arms like this. But show the crap. Turn this way. Turn this way. Now, you guys aren't a liquid anymore. You can't move. You're kind of rigid. Now you're not a liquid. You're a... Very good. Go sit down. So, give them a round of applause. If you learned anything today, I hope you learned that gases, the molecules are far away and they move fast, and as you pull them down, they get slower and they turn into a liquid, eventually into a solid, okay? Now, why do I bring this up? Water is an amazing substance, okay? Water, who knows what water boils at in Fahrenheit? Don't ask me Celsius. Celsius is easy, actually. Yes.
212.
Yeah, you're my man. You are going to be a cook one day. Water boils, turns from a liquid into a water vapor at 212 degrees Fahrenheit. Does anybody know Celsius?
100.
Yeah, 100 degrees Celsius. Now, here's why water's amazing. Water is a gas at 212 degrees Fahrenheit. When does it, and then it's a liquid. So 211 degrees, it's liquid, 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 liquid. Well, once you hit 212, we're getting into gas, right? So all the way down to when does it become a solid? 32 degrees. So water has this amazing amount of temperature range where it's a liquid. That's what makes it really great, okay? Now, we were talking about nitrogen. Nitrogen is very different than water, okay? Nitrogen doesn't even become a liquid at 32 degrees. When water becomes a solid, nitrogen is still a gas. So we still have a whole state of matter to go. Nitrogen doesn't become a liquid until super cold. What's the coldest temperature you think you ever felt? You on Earth, here. What do you think?
0 degrees.
Not your turn anymore. I know you're revving up, but let's get this guy in. Coldest temperature you ever felt? Gets cold here in Connecticut. 20. Lower than freezing. Liquid nitrogen? Not happening yet. Come on, give me colder than that. Colder than 20. 6 degrees. It's freezing. I feel like it's cold outside already. Much colder than that. The coldest temperature you think on Earth? What's the coldest temperature? Like Antarctica on January 31st. How cold?
0.
0. Colder than 0.
Negative 1.
-1. Keep going.
Negative 1,000.
Negative 1,000 does not exist, actually. I learned that absolute 0 is negative 400 and something, 480, something like that. But so there's no negative 1,000. Once you get to negative 400 and something, that's absolute 0. It can't. We don't know anything any colder. So nitrogen doesn't turn to a liquid until negative 320 degrees. Which is absolutely bananas. Now here's my disclaimer as I'm going along here. Luckily, we have an amazing container here filled with radioactive, no, I'm just kidding, filled with liquid nitrogen. We have a container that can travel, who knew? It was in my car, they cracked the window, they say. Filled with liquid nitrogen, okay? Here's my disclaimer. Normally, I would do the ball experiment last, but because I was warned that we're running really low on liquid nitrogen, there might only be enough to do this awesome experiment. So, there's a second one I want to do in case we run out. And to be fair, I haven't opened that since they poured it in there, so if it's empty, we'll use our imaginations. But I have 3 balls here. What kind of ball is this?
Orange.
Well, that's the color, but anybody know what kind of ball this is? Yes?
A big ball?
It's a ping pong ball, right? Okay, and it bounces. Let me use my trusty hard plate just in case you didn't know. Just like a ping pong ball. And you guys have seen these before. You get these in your little machines for the coins. What is this? A bouncy ball, right? Rubber bouncy ball, right? And then the adults might play a little of this, every once in a while on a business meeting. A racquetball, a little squash. I actually play darts with a squash instructor. It's very interesting. Squash all day long, every day. All right, so you saw me bounce them all there at the normal room temperature, right? But when you use a super cooled liquid like nitrogen, weird stuff can happen to normal everyday items when you dip it in that. So let's find out what happens. Let's get some hypotheses. So we'll start with the ping pong ball. Let's just cross our fingers that there's plenty in there. I'll use my handy dandy gloves here. Okay. This is the part you do not want to try. Probably okay. Please don't. Oh, I hear sloshy. That's good news. That's good news. So, now luckily also we have this cup here that is supposed to also, you're going to notice something right away, boys and girls, when I pour this. Okay? I feel like Richard Blaze, if we have any Top Chef fans. Okay, what is going on? Yes, young lady.
Smoke.
Smoke. It's actually some sort of gas, right? It's not smoke necessarily, but it is gaseous. Well, why is it gassing up like that? Yes.
That's called steam.
Not steam. I didn't heat it up. I actually cooled it down, but you're on the right track. It's made out of the same stuff as steam. It's water vapor, right? But what is it? Remember what we said. We have oxygen, carbon dioxide, nitrogen, and water vapor, gas water in the air. That stuff is so cold, I gotta not talk so much because I don't want it to all evaporate on me, that as soon as it hits the air, it's taking all of the water and it's skipping over the liquid process and it's turning it right into a frosty steam. Now, we'll start with the ping pong ball. What's gonna happen when I take my tongs and I dip it in the ping pong ball? Yes, what do you think?
If you take it and drop it on the ground, it'll just shatter.
It's gonna shatter. Let's see if he's right. So I'm gonna put it in there for a second. Does anybody else want to take a different guess? He said I'm gonna drop it and it's gonna shatter. What do you think?
I think it's gonna go
You think it's gonna float? That'd be awesome. Anybody else want to take a guess? Anybody on this side? I'm focusing a lot on the kids in the corner over here. I'm sorry, you guys. What do you think, Christmas tree? What's gonna happen to my ping pong ball in the super cool liquid?
I think it's gonna float.
You think it's gonna what? Float? Forgot the float. All right. Let's see what happens. Ready? 3, 2, 1. That should be enough. All right. So I'm gonna bring it over, show you guys. All right. Don't touch it. All right. So just by looking at it, observing, what's anything? You notice anything happening? Anything happening to it? What do you see? All right, so what did you notice? Yeah.
Smoking?
Yeah, it's kind of, this is what a comet looks like, boys and girls, in the night sky. Why the comet has a tail is because it's so cold that it's gathering any of the water vapor in the atmosphere and it's instantly freezing it. And so it looks like it's smoking. And literally it's going to change color and it's going to get some frost on it, just like your lawns will tomorrow. So, unfortunately, they say. But now let's bounce it. Shouldn't be. Kieran's eyes just lit up. All right, let's see. Ready? All right, here we go. 1, 2, 3. Oh, nothing happened. That was kind of lame. All right. We have 2 more balls, Kieran, don't worry. So, now we have the bouncy ball. That one bounced kind of normal. I don't know what happened. We'll try this one now. Bouncy ball again. We'll do the test. It bounces just like a normal bouncy ball.
It goes out for too long.
I'm going to go back to Kieran because his hypothesis was incorrect, and we're going to have to see if we can correct it. Kieran, now this one I have in here. Unfortunately, the ping pong ball just bounced, right? It was a little lame. What do you think is going to happen with this one?
I don't know, but I'm changing my hypothesis.
Changing the hypothesis. What do you think?
No, to the racquetball.
To the racquetball. What's going to happen to the racquetball?
It's gonna shatter.
Now, why did you change your hypothesis?
Cause I know the ping pong ball. I think it was too thin, maybe outside.
Too thin. Okay. Okay. What's different between the ping pong ball and this bouncy ball that I have?
Oh, it's too
Yes.
thin.
Made of rubber, and the rubber is all inside of it.
This group is awesome. It's made of rubber, different than plastic, and it's not hollow. The rubber's all inside of it. So it should act differently. Let me continue. What's your name? Aaron? Aaron, what is going to happen when I drop it? Okay.
But it's going to.
Let's find out. Should we find out? All right. I took it out again. It's smoking. I'll show you quickly. I don't want to. All right. Same kind of. It's still gathering all that water vapor that's in the air. But now let's drop it. All right. I'm gonna really bounce it. See if it's gonna bounce. 3, 2, 1. Bounce, nice. But do you notice the difference in the sound? What does it sound like? Yes.
Plastic.
I wouldn't even say plastic.
Metal.
Maybe like glass.
It sounds like a marble, right? Or a rock.
metal.
Okay?
Sound like metal.
Or a metal. It's really, really solid. So even though it still bounces, it definitely doesn't have the same feel to it than the first time I bounced it. Well, we've got one more left. How are we doing in there? Now this is a trick that they always play on me, just for fun. These were not white when I started, boys and girls, so that's interesting. You know what that is?
Frost.
It's to frost. All that water that's in the air is now clinging to my metal tongs, okay? Now this is the funny part. Now this fits in here, but then it's like a sideshow trying to get the racquetball out of the thermos, and so I'm going to do the best I can, but let's get it in there. Now Kieran changed his hypothesis. He said, this has got some frost on it too, if you want to see. He said, I don't think it's going to be the ping pong ball that shatters anymore. I think it's going to be the racquetball, maybe because the racquetball is thicker, and so maybe it's going to shatter. Does anybody else have a different opinion? Are they both hollow? Yes, they are. Well, one's made out of rubber. This one was made out of rubber too. So this one's hollow like the ping pong ball, but rubber like the bouncy ball. What do you think might happen? Anybody else want to take a guess? Yes, Arlen.
It may shatter, it may bounce, and then go down again and shatter.
Maybe it'll bounce and shatter. All right. Well, we're gonna have to try and find out. All right. Let me just make sure we get nice and cold in there. Now, what was I gonna say? Let's see. See, and this is why we always run out. I can't. It's like one of those sharper image puzzles to try to get the dollar out. And that's why I am going to.
Make a big
Which is
mistake.
blue. All right, you already heard it. So here it is. All right. Oh, quickly, it's we'll put it out here like this. We'll put it on. And so now, obviously, it's the last one. And so I was going to tell you, logically, it makes sense. If I'm trying to put on a cool show, I want to want the coolest thing last, right, Karen? So that's really the logic we're thinking, right? It needs to be the last one. The last one will be the coolest thing to happen. Well, let's try and bounce it. 3. Count me down from 3.
3, 2, 1.
Don't touch that. So, Karen was right. Give Karen a round of applause again. As you can see, crazy stuff happens when you have super cooled liquids. It shattered just like glass. Now, why did that happen? Which one of my child scientists in here, which is an amazing group, by the way, all the parents should be super proud of them. I mean, I'm proud of them. I'm going to pour this in here so we can keep it so I can do my last experiment with this if we want. Sue, can I go long? Is that like okay? Or? Okay. Do I have more in here? Let's see. Oh, good. We'll do another experiment if I can get it. Why did
There's 2 little pieces that from the ball.
Oh, thank you. Let me see. Now, don't try this at home, but
We don't have
it's
to.
really, you know. As long as you're careful. Why did it shatter? Yes.
Because,
Aaron.
like, the outside was hollow.
Okay.
The frost made it so cold
Yeah, give me more.
that it just, when you dropped it, the frost became more frost and it just dropped and it shattered.
The molecules actually changed their structure because they got so cold. Rubber is flexible, right? Everybody do this. Right? When you throw rubber, you're going to bounce it. It's going to have some spring to it, and it's going to bounce. It's going to, at room temperature, right? It's going to have no trouble moving its molecules around. But when you make it super cold, the molecules are getting so close together that they're not flexible anymore. They become something called rigid. Okay? Rigid means really, really hard, but also fragile. So even though they're hard, they're much more likely to shatter or break. Okay, and that happens when you make things cold. Yes?
I was just wondering, does the air inside of the ball, if it's hollow, have anything to do with it?
That is a question for Dave Mestry, our astrophysicist.
Mm.
So, I've never been asked that before, but I'm going to find out the answer to
Okay.
that. I don't know, to tell you the truth. I think it has, from what I was told when I was trained in this demonstration, is it has more to do with the rigidity that is happening to the molecules of the rubber.
Right.
So, and if that was the case,
It's probably not the major thing, though. Just curious if it had
but
any
the ping pong
impact.
ball, I'm thinking, then why didn't that shatter? Because the air is happening the same in both of them, right? It's definitely condensing inside a ball. So.
And temperature. Yeah.
It's a porous surface, the air will contract and will suck more in and will equalize.
Oh, okay. So you should be asking him. I'm here for this crowd. Okay, how am I doing so far? So far, so good? Okay. All right, now, let's talk more about that. So, like I told you, I want to make sure I got that one out of the air. Yes, young lady?
The ball pieces out a little bit blue and more white.
You know what that white is, right? That's that water in the air that is frozen onto the ball. Now I have a balloon here. So now there is a finite amount of air I can put in this balloon, right? That's the air I put in the balloon, and now if I let it go, we'd actually have a crude rocket, right? But instead I'm going to tie it off. Now, my best friend still can't do this, but I'm proud of myself that, you know, if there are enough birthday parties, I have no trouble tying off the balloon. Can I put any more air in this balloon right now?
No.
No, right? I'd have to untie it, right? So you know that this air, the air in this balloon is all the air that can go in here, and it has been filled up, right? Can I take the air out of this balloon?
Yes.
Sure, how?
Pop it.
I could pop it. Could I take the air out of this balloon if I didn't pop it?
Yes. No.
How?
If you untie it.
If I untie it. Okay, so we've come to the conclusion that there's legitimately two ways. It'd be hard to do, I think, but I could untie the knot and let the air out, or I could pop the balloon and let the air out. Other than that, is there any other way I could let the air out?
Could teleport it.
What?
Maybe Elon Musk might be able to pull that off someday. Now, so keep that in mind. And now watch what's going to happen to the balloon when we put our liquid nitrogen on it. Remember what I said. I'm not putting any more air in. I'm not taking any more air out. You know what? I think it's actually safer. Pour some of this in here. There you go. Look at that water vapor instantly condensing. That should be enough. I'm so happy there's enough in here. Here are my tongs. I'm going to hold the balloon by my knot. And we're going to pour it. So, you all said I cannot. Let's take a couple guesses. What's going to happen when I pour the super cool liquid onto the balloon? Yes, Aaron. It's going to pop. It's going to get so cold. Anybody over here? Yes, young man. What's going to happen when I pour the super cool liquid onto it? It's going to pop? You agree?
I don't like popping.
Yes.
Force it open. Force it open.
It's going to force it open. Well, let's see if you're right. Now,
I don't like
I mean, it could do that, but instead it's
Yeah,
a
it's
little
gonna
more
contract.
like what? Oh, it didn't pop necessarily, but it looked like it did what? Now, you know, did I take air out of this balloon?
No.
No, I didn't. So why does it look like I took the air out of this balloon? And if I didn't take air out of it, am I putting air back in it?
No.
But yet, why does it look like I'm putting air back in it? What just happened? Any idea? I'll give you a hint, boys and girls.
I think
We already went over this. Yes.
maybe a chemical reaction.
I wouldn't say it's no chemical reaction.
it.
No, not a chemical reaction. A temperature reaction. Okay? You came up here, you stood over there, right? Gas is far away. Expand the whole balloon. It's pretend that our two boys were in this balloon, but they were far away from each other. And then I poured that cold water on them. What did I do to them?
Hold them together.
I brought them together, but now all that space that was in between them is not there anymore. So all those molecules are taking up less space, less space, less space. The colder you make the gas, the less space it's going to take up. So the balloon is going to shrink. It's going to almost look like it's melting in size. But then instantly it re-expanded. Why? Why did it re-expand? So fast. Yes. Exactly. If I stopped pouring the super cooled liquid on the balloon, what does that mean for the temperature of the balloon? Yes. It gets warmer. Give her a round of applause. She's awesome. And since the air temperature in the room is close to 400 degrees hotter than liquid nitrogen turns to a liquid, it almost instantly burns off. So even though we made it super cold, it instantly went back to normal temperature again. And so those molecules went back to doing what they were far away from each other, so it re-expands. So it shows you how matter works in a very, ordinary way. Last thing, don't try this at home, right? So what do we got? We're done with our liquid nitrogen. Hallelujah, there was enough that lasted in there, and I didn't give myself frostbite. That's good. So let's continue to talk about air, but instead of cold, let's talk about hot. What's really hot? Fire. Let's make a fire. Don't try this at home. So, oh no.
I don't know.
I can't make the fire today. My fire making material didn't make it into the kit.
I know what makes fire.
I was so bummed.
2 sticks.
All right, well, we're over anyway, and I'm glad we're over anyway. So, I can't make it appear.
Use 2 sticks.
I almost want to keep it here and be like, but it's not in the car, and I'd feel really
Use
bad.
2 pieces of metal, you can make a smoke.
All right. Let's talk about the 3 things that need to make fire. And so if you come to the museum and you see this demo, which we do basically, a weekend or 2 every month, okay? We're gonna talk about the fire. So what do you need to make fire?
2 sticks.
The sticks could be part. Sticks could be 2 parts of it, actually. What do we need to make fire? Something to do with the air. Yes?
Heat.
Heat. Well, we do. We need a heat source, a spark. That's one thing. Yes, here. Yes, a spark, right? And you 2 are working together really well today. Yes?
Wood.
Wood would be the fuel. In this case, it was going to be a candle and this other super cool powder that didn't make it into my kit. And oh God, you're the man. I'm the best. What do we breathe? Oxygen. To make fire, you need oxygen, you need a spark, and you need fuel. Okay? So, I can't do it, but I had fuel for the fire, and I was going to show you how I was going to try to light it on fire, and it wasn't going to light. But so you're going to have to come to the museum to see that last fireball experiment. So that is it for the Don't Try This at Home experiments today. I hope you enjoyed it. Now that we have a whole group of people today, out of the kids, who has been to the Discovery Museum in Bridgeport before? 1, 2, 3, 4, 5. Okay, excellent. Come back and see the rest of this demo. Not only do we have the fireball, but we have a Tesla coil that creates electricity in the room. And we have a brand new planetarium system. State of the art, it's better than ever, it's amazing. You've got to come back to the Bridgeport Planetarium at the Discovery Museum. So, I want to thank you all for coming today.